In this video, we present Proof of Concept 6 for the MARE project. This demonstration outlines the implementation of a zero-touch security framework designed to detect and mitigate telemetry data poisoning directed at the Network Data Analytics function, or NWDAF. The NWDAF's primary function is to aggregate and process event data generated by various network functions to supply network-wide analytics. In the MARE architecture, these resulting metrics are forwarded to a centralized telemetry component. To maintain prediction accuracy, the models used by the NWDAF to analyze the telemetry are continuously retrained. What would happen if the analytics exported to the security plane stopped being reliable? For the purposes of this demonstration, the monitored metric is the abnormal behavior indicator, specifically the suspicion of DDoS attack exception. Under normal conditions, if a DDoS attack occurs, the telemetry from the affected network function exhibits anomalies. The NWDAF processes this data, correctly triggers the exception, and exports the metric to the security plane to initiate mitigation. The continuous model retraining mechanism, however, introduces a vulnerability to data poisoning. In the proposed attack scenario, an adversary compromises a network function or intercepts the communication path to the NWDAF. The objective is to inject tampered telemetry into the data stream. By subtly altering the data over an extended period, the attacker manipulates the baseline parameters that the MTLF relies upon for DDoS detection. Examples include injecting inflated traffic volumes into application function events, or falsely reporting higher user equipment counts via the AMF. The consequence of this manipulation is that when the attacker eventually executes a DDoS attack, the system fails to detect it. The poisoned model, having integrated the tampered data into its accepted baseline, misclassifies the abnormal traffic volume as benign network activity. The security plane subsequently receives no alerts, and mitigation measures are not deployed. To address this vulnerability, an automated, closed-loop remediation architecture has been implemented. This pipeline connects a security-enhanced NWDAF, which exposes specific threat remediation endpoints, to the closed loop, referred to as Zero-Touch Security Framework. The framework monitors the NWDAF's data streams for tampering evidence. If poisoned data is identified, the system automatically transmits remediation instructions back to the NWDAF's endpoints to isolate the compromised data source. If the isolation of this source reduces the remaining data volume below the threshold required for accurate analytics, the system suspends the analytics subscription entirely and issues a notification to the security plane. Operationally, this process executes across 4 sequential stages: monitoring, analysis, decision, and execution. Telemetry is first ingested, evaluated by a tampering detection model, mapped dynamically to a predefined mitigation playbook, and finally executed via an OpenC2 actuator that interfaces directly with the NWDAF. We now proceed to the deployment and demonstration of this architecture. Upon initial deployment, the OpenTelemetry agent establishes a subscription to the NWDAF. The purpose in this subscription is to export the abnormal behavior metric to the centralized telemetry stack. Subsequently, the analytics logical function submits a data acquisition request to the monitoring platform, which subscribes to the events of the relevant network functions. As events are emitted by the underlying network functions, they are collected and persisted within a time series database. These events are then utilized by the NWDAF to compute network analytics. The generated analytics are exported to the MARE telemetry by the OpenTelemetry agent. Following the continuous ingestion of telemetry by the NWDAF, the Zero-Touch Security Framework initiates its monitoring stage. This component interfaces directly with the time series database to extract a rolling window containing the most recent 30 seconds of telemetry data. This batch of data is then forwarded to the analysis stage, where it serves as the input for the AI/ML tampering detection model. The model evaluates the data stream and outputs a structured set of predictions regarding the tampering of the ingested telemetry. If the model's predictions indicate a high probability of data poisoning, the analysis stage emits a security alert. This alert is transmitted to the decision stage, which is responsible for dynamically mapping the identified anomaly to an appropriate mitigation playbook. Once the correct strategy is selected, the playbook is passed to the execution stage. Here, the playbook interpreter parses the documented workflow and translates the required mitigation steps into standardized OpenC2 commands. These commands are then dispatched to the OpenC2 actuator for enforcement. Upon receiving the OpenC2 commands, the actuator enforces the requested countermeasures. Once the OpenC2 actuator triggers the security-enhanced NWDAF mitigation endpoints, the final stage of the mitigation workflow begins. First, the NLF isolates the compromised data stream, preventing further integration of poisoned data into the analytics pipeline. Then it issues an instruction to the monitoring platform to explicitly disable the associated data collection jobs. Finally, the system evaluates the remaining volume of trustworthy data. If isolating the malicious source degrades the data volume below the threshold required to compute accurate metrics, the system autonomously pauses the analytics subscription. In summary, this demonstration validates the efficacy of the zero-touch security framework in protecting the security-enhanced NWDAF against telemetry data poisoning. By autonomously detecting and mitigating tampered data ingestion in near real time, the system preserves the integrity of the machine learning baselines required for accurate threat detection. This automated, closed-loop architecture successfully neutralizes the vulnerability before an adversary can leverage it to execute subsequent undetected attacks, sustaining the overall resilience of the network. This concludes the demonstration for Proof of Concept 6. Thank you for your time and attention.